Today in Science from Wired.
Why is our solar system flat? It started as a big old ball of dust, so how did it end up like a giant pancake? Get the true story using fake forces. By Rhett Elaine. Why is the solar system flat? Let's talk about some physics. There is an attractive gravitational force between any two objects that have mass. You have mass and the Earth has mass, and it is that interaction that pulls you toward the Earth, so your feet stay on the ground. The magnitude of this gravitational force, represented by a capital F, depends on the values of the two masses, let's call them capital M and lowercase m, and the distance between them, lowercase r. But the solar system contains more than two masses. In fact, it started as a big cloud of dust without any planets and without the sun, and every speck of dust had an attractive interaction with every other speck. That's a lot of complicated stuff going on, but there's a trick we can use to simplify it. If the dust is evenly distributed, then a particle on the outside of the cloud would experience a gravitational force as though all of the other dust was concentrated at a single point in the middle of the cloud. So what would this giant cloud of dust do? Well, each piece would experience a force pulling it toward the center of the cloud. It would essentially collapse in on itself. The cloud of dust that formed our solar system started off with a slight rotation. Why does that matter? In order to answer that, we have to think about what happens when an object moves in a circle. Imagine you have a ball attached to a string and you swing it around in a circle. As the ball moves, its velocity changes direction. Since we define acceleration as the rate of change of velocity, this ball must have an acceleration. Even if it's moving at a constant speed, it will be accelerating because of its circular motion. We call this centripetal acceleration, which literally means center pointing, since the direction of the acceleration vector is toward the center of the circle. See, words make sense sometimes. We can also find the magnitude of this centripetal acceleration. It depends on both how fast the object is moving, represented by lowercase v, as it speeds around the circle, and the radius of the circle, represented by lowercase r. However, sometimes it's more useful to describe circular motion with angular velocity. The linear velocity, or lowercase v, measures how far an object travels in a unit of time. Angular velocity measures how much of the circle it traverses in a unit of time. How can we measure that? If you drew a line from the center of the circle to a starting point and another line to the ball's position after a second, those two lines would define an angle. So angular velocity measures the angle that the ball covers in radians per second. It basically tells you how fast the object rotates around a center point. With that, we get the following two definitions for centripetal acceleration, or lowercase ac. It's important for dust particles in the early solar system. If they're moving in a circle, then they are accelerating. But now let's do something a little dangerous. Let's think about fake forces. First, imagine you're standing in a stationary elevator. There are two forces acting on you, the downward gravitational force and the upward pushing normal force from the floor. Newton's second law says the net force on an object, like you, is equal to the mass times the acceleration. If the elevator is stationary, the acceleration is zero, and that means the floor has to push up with a force equal to the gravitational force so that the net force is zero. Now, suppose you push a button and the elevator starts to zoom upwards. Since the acceleration is no longer zero, the floor has to push up more than gravity pulls down in order to have a net force that is not zero. That's all fine, nothing fake about those forces. But there is another way to look at this. It's possible to describe how stuff moves with respect to the reference frame of the elevator. However, the elevator is accelerating, and Newton's second law doesn't work unless everything is measured with respect to a non-accelerating reference frame. We call this an inertial frame. We can make things work in the non-inertial frame by adding in a fake force. The fake force would be in the opposite direction and would equal your mass multiplied by the acceleration of the elevator. It's a fake force since it's not actually due to an interaction between two things, but humans like these types of forces. It's a simple way to explain why you feel heavier in an accelerating elevator. What if instead of a human in an elevator, you were a ball attached to a string moving around in a circle? Using the reference frame of the ball, there are two equal forces. The string pulls toward the center of the circle, and there is an outward pushing fake force. In this case, we call the fake force the centrifugal force, which means center fleeing. It's the fake force you experience that pushes you outward when you take a fast turn in a car. It's just like the centripetal force, but in the opposite direction. If you increase the angular velocity, the centrifugal force will increase. If you make the circle that you're implicitly traveling around smaller, like a hairpin turn versus a long gradual curve, the centrifugal force would also increase. What if we want to create a solar system from a giant cloud of dust that is slightly rotating? One particle is on the equator of the rotating cloud and another is near the top, close to the axis of rotation. Both experience the same magnitude of the gravitational force, but in different directions, and they have the same angular velocity since they are in the same rotating cloud. In the reference frame of the rotating cloud, the two particles of dust will also have a fake centrifugal force acting on them. Okay, let's review. The solar system started from a slightly rotating cloud of dust. Particles near the equator found a stable circular orbit as the inward pulling gravitational force was balanced by the outward pushing centrifugal force. Particles near the poles had less centrifugal force, so they got pulled down toward the middle, forming a big flat disk. Those at the poles had no centrifugal force at all, so they got pulled into the center of the solar system, where the sun would eventually form. There's really no such thing in physics as a centrifugal force. It's just a feeling you get when you're moving around in a circle, like on some crazy spinning carnival ride. But you know what? Sometimes we can tell a true story using fake forces. Thanks for listening to Wired. My name is Zeke Robison.